Okay, we're going to look at exam 1 for organic chemistry 2. This exam is going to be covering, or was covering, basically chapters 11 and 14, along with, as usual, a review of the previous chapters. So let's take a look at page 1 here and see if we can work through. So we're asked to basically fill in the blank here with either the reagents or the products for each reaction. So let's start to take a look at the top here. So we're asked to take an alkene, right? We're asked to take an alkene into a diol. There's a couple ways we can do that. The most straightforward way, I guess, is we can just use osmium tetroxide. We could have used, KMNO4 when it's cold and dark, and or we could have made an epoxide and ring opened it. So there's plenty of ways to do this, but let's just stick with osmium tetroxide. Okay. Now, for the next part, we're taking a diol and turning it into a set of aldehydes. So we need to do let's say, a soft or an incomplete oxidation, right? We need to do an oxidation without water around, PCC or PDC or a Swern oxidation or DMP. Any of these would have been acceptable answers here, right? But PCC, we'll just go with that. And then in the final case, we need to do a conversion of an aldehyde into a carboxylic acid. And so there we need some, let's call it harsher oxidative conditions. So we need our chromium salts, and we'll put it, with some acid and water, right? So we'll generate, we could have put chromic acid, H2CrO4. That would have been essentially the same thing for us, right? And there we go. So a diol, a vicinal diol in blue, we do a soft oxidation or an incomplete oxidation maybe, or whatever you want to call it, to take an alcohol, a primary alcohol, into a set of aldehydes with PCC or PDC or DMP or a Swern oxidation, and then the last step we finish the oxidation. All right, so next we have a tosylate group and an alkene, and in the first step there we want to get rid of our tosylate group and we want to replace it with a hydrogen. Now what do I mean by hydrogen? Well, if we take a look here at our starting material, right? Our hydrogen in blue stays there, but our tosylate leaves. So what does that mean? That means our incoming group has to be a hydrogen, right? And if we want to displace a tosylate, we're going to need a good nucleophile to kind of come in and do that, right? We're going to need an H with a minus charge. And so to do that, we could use sodium hydride, or LAH would be fine also. Although LAH is a bit excessive, but I think it'll be fine in this case. Okay, so either one of those would be fine, right? We need an incoming hydride. Last step, we need to make a vicinal dihalide. So we know we're going to need some Br2, and we want to prevent the formation of radicals, so we want to keep it cold and dark. Right? Not too bad. All right, next. We have a primary halide with sodium hydroxide and water. So sodium hydroxide, right, this is a strong base. This is a strong base and a pretty good nucleophile, an unhindered nucleophile. And we have a primary leaving group here, right? So this is all set up for an SN2. All right, so that's going to hit and pop that out. So we end up turning a halide into an alcohol. There it is. Just make that a little bit neater. Wonderful. Okay. Next, we're going to use sodium hydride and THF. Now remember, sodium hydride has one main purpose in life. I'm not saying that it can't be used for something else, but its main purpose in life is to act like a good base, right? And here we have let me change colors. Here we have a acidic hydrogen, and we have a very strong base, right? So the first reaction that's going to happen is a deprotonation, right, where we turn an alcohol into an oxygen with a lone pair and a negative charge. Okay? Now what do we know about oxygens with lone pairs and negative charge? They tend to be strong bases. They tend to be decent nucleophiles if they're not too sterically hindered, right? And if we put these two together here, right? All right, we can't do an elimination, so all we can do in this case is a SN2. And so we end up making this guy. So this is a classic Williamson ether synthesis, right? This is classic Williamson ether synthesis. We have an alcohol we put in the presence of sodium hydride, and then we put in some primary alkyl halide to make an ether. Oh, sorry about that. Kind of zoomed in there for no reason. All right, next. So we have an alcohol with PBr3. So we're just going to swap out our alcohol for a halide. And we looked at the mechanism of this, right? The phosphorus acts as a good Lewis acid, right? The alcohol attacks the Lewis acid, generates a good leaving group, and the bromine comes in. Now when you put a halide, let me change colors. When we put a halide in the presence of magnesium or lithium, right, we end up forming some of our Grignards or organolithiums, right? In this case, since we're using magnesium, we're going through a Grignard route there. Good stuff. We're carrying on with that same compound down here. We're going to assume that this acts as a good nucleophile, although we'll learn a little bit later in the semester some other reactions that we can do, right? I'll just write it like that, it looks a bit cleaner. All right, so we'll assume that we act as a good nucleophile and hit that carbonyl carbon. And then in the last step, this is a Swern oxidation. And so we just take our alcohol and put it into a ketone here. Okay. All right, so that's page 1. I'll just zoom out of here for a minute so you guys can take a look through that. And we'll move on to page 2. All right, so let's look at the top here. So we got an epoxide, we got an organolithium, right? So we're under basic conditions, right? These are strong bases here. Remember when you see an organolithium or you see a Grignard, what we're really seeing is a lone pair and a negative charge on that carbon, wherever the lithium or the magnesium bromide is. Extremely powerful bases, good nucleophiles in some cases, or in a lot of cases, I should really say. So when our basic conditions, so we're going to ring open by hitting the less substituted side. Right? We're going to ring open by hitting the less substituted side. Right? So there's our carbon that we hit. Okay. Now I'm going to pause here. That carbon is that carbon right there. One of the most missed parts is how we miscounted our carbons. Right? Don't forget that one carbon right there that we hit. Okay. So count your carbons. So remember basic conditions. We act SN2-ish, right? And SN2-ish, we hit the less substituted side of the epoxide to ring open. All right, now we got a cyclical epoxide, and we've got acidic conditions here. So we're going to ring open. Whoops, I didn't mean to draw a 6-membered ring, pardons. All right. So we're going to ring open. We're going to add an alcohol. And we're going to add our carboxylic acid here to the other side as an acetate group. And don't forget, right, that we will make both enantiomers here, okay? Not both enantiomers, I should say the set of enantiomers. So let's quickly take a look at let's take a look at this mechanism. All right, so we start out here, right, with H+. This would be an adequate way of starting. So we end up with our protonated epoxide. Our carboxylic acid then can come in. This oxygen here is going to actually end up doing the heavy lifting, so to speak. And it's a great question as to why that is. And you guys can figure it out for yourself here in just a minute. But let's draw the product of that step. And let me make this dashed here, sorry. Okay, so that's our product after that step there. And here, to answer my previous question, or to look at, right, look at this intermediate right here and say, why did we use that particular oxygen? Right? Why did we use that particular oxygen to come in and act as a nucleophile in this case? Right? My hint to you is draw resonance structures. All right, in the last step then, something will come around. We'll just use some water in this case. We'll use some water in this case to come and kind of clean things up. So we'll do this. And that will get us to our product. Sorry, I ran out of room over here. Okay. Wonderful. You didn't need to do the mechanism, I'm just showing it to you guys. Fantastic. Next. We have an alcohol, we have sulfuric acid and high heat. That's setting us up for an acid catalyzed dehydration. So we end up turning an alcohol into an alkene. And then HBr, easy peasy, right? We do an addition reaction. We're under acidic conditions, so we end up adding our halide to the more substituted side, right? So we have a Markovnikov addition. Right, we have the same starting material here, right? So another alcohol with thionyl bromide, right? Those are our conditions to end up generating turning an alcohol into a halide. And then in our next step here, right, we've got a strong base, right, an oxygen with a negative charge. We've got a strong base and a secondary leaving group, right, strong base with a secondary leaving group here in our starting material. That's all set up for an elimination, right? This is all set up for an elimination. Strong bases with secondary leaving groups are going to favor our elimination mechanisms, specifically E2, right? So there's our product. Cool. So I'm going to zoom out. There's our stuff here. We'll stop this video here and we'll pick up on the next video with the remaining pages.